So this book that we distributed, back when we had COVID and we couldn't get our team together, we can only have maybe 2 people at a time. We decided that we really needed to write stuff down and try to get a better way of teaching the students, because originally we had an actual workshop every day that we met, and we would get in a classroom and we had a blackboard and we would talk about calculating stress and angles and such. So we got to work with everybody, and it was a really pleasing situation, and they learned a lot. But all of a sudden we couldn't get together, so we couldn't do that. So we tried to put that in a booklet, and I call it the handbook. So it talks about the tools and the mechanical things that you have to do to develop a solar car. And the things I'd like to talk about are mostly related to building a solar car. One is the safety aspect. You know, if you're going to build a car, you really need to have a clean, spacious place to work. It's really important that you're not tripping over wires or pieces of equipment or materials. So you need to find some garage type situation where you can have the car and have plenty of room to walk around it, and you want a place that's safe and not subject to being rained on or blown away. And it should be something you can lock up, because you're going to end up with a lot of expensive material and equipment inside the structure. So, you know, that's one of the things you need to do. The first thing is read the rules. It's really important that you sit down and read the rules as a group and go over what you think you need to do to build a car. And then you have to decide on what class you want to race, because there are several different classes, and probably should start with a simple class and not a more complicated class. The things that I would recommend you do for a basic design is, first, once you've decided the class you're going to run and a basic design, then you're going to have to look at what wheels and tires you need. And that's almost the first thing you need to figure out, because the size of those wheels and tires determine a whole bunch of other things. Then you need to figure out what wheelbase you're going to run, what front track you're going to run, and what kind of chassis you want. And there's all kinds of different chassis, so we'll talk about that in a second. Then you're going to have to think about a basic body. Do you want to have a body? Not necessarily do you need a body. Do you want to have some wrap that goes around the structure to make your body? Do you want to make a fiberglass body? That's a time-consuming thing. So all these decisions you got to do early, and then you got to think about the motor you're going to use, what drive you're going to use off the motor, what kind of suspension you want to have. For instance, we've run cars for I've been involved in this for 7 years, and we started with independent front suspension, but recently we built a car with a straight front axle, which has some advantages and a few disadvantages. So you have to think about that. What kind of steering you want? Do you want something that goes out to both sides of the car, or has one side steers and has a drag link that goes the other side? These are all basic things that go back to when people used to make horse and buggies. You know, what kind of steering you want. And that kind of information is talked about in this little handbook. And the fact that you probably want some Ackerman steering involved. That's going to have the wheels follow up the turn radius that the car's turning. They're different, because the inside tire is going to follow a tighter radius than the outside, so you have to have Ackerman steering. So that's explained a little bit. And of course you can do all kinds of research of these things on the internet, and multiple books are written on suspension. What kind of array you're going to run, you have to decide that. That makes a big difference on how you're going to mount the array, because some of these systems arrays are really lightweight, and some of them are quite heavy. So the ability to tilt the array is an important thing. So all these design considerations are a big deal. And finally, you have telemetry, depending on what kind of components you buy. We talked about the MPPTs and some of the motor controllers, and some of those have feedback loops, and you can tie into that and get all kinds of information for your telemetry. But one of the things that you need to learn, these new students and I found this out with the recent team we're working with, their background on tools is really limited. So we came up with a board, which we have over here, that has the basic tools that you use to build a solar car, like a hacksaw and a screwdriver and a wrench. And we actually put samples on there and screwed them to the board and put a label on there, and that helps a lot. That way, the students, when they come in, some of them have never worked on anything. It's going to be their first experience. They don't have any idea what the tools are called. So your first task is to teach them what the tools are, what they're called. Then you have to teach them how to use the tools and how to use them safely, because you can get hurt using any of those tools. You can round off your knuckles, or you can cut your fingers, and so you don't want to have any of those kind of experiences. So if you take time to work with the students and teach them how to work the tools, start with the hand tools, that's a really important thing. And once they learn how to use those things, then you'll have some confidence in letting them go off and work on whatever they need to work on. So you don't have to stand over them and make sure they don't hurt themselves. We only had one injury in the 7 years that we were building cars, and it was from a father stepping on a daughter's toe and breaking her toe. So that was not really our fault, but she did really get a nasty break, and that was kind of unfortunate. I used to work at Texas Instruments. I started there after I got out of college, and they had a program. They had a complete machine shop with lathes, mills, practically everything you can think of, and they call it the model shop. And in that model shop, if you were an engineer at TI, you could work in there on anything you wanted to work on, and they even supplied all the materials. So if you needed a chunk of aluminum and you wanted to put it in a mill and make something, you were more than welcome to do that. They had all that available. However, in order to use that machine, you had to be trained on the machine. And once you learned how to work that machine, and the machinist that worked there, who was in charge of that model shop, he would give you a little card, and it would be stamped and say that you were approved to use that. And we're talking hand grinders, electric drills, lathes, mills, everything. So once you got where you were trained, and they trained you and certified, you could use anything in the shop without any problem. Of course, nowadays when you get kids that come in, they've never used a grinder before, they've never used a bench grinder, and they never used a table saw. So all of those things are quite dangerous if you don't know how to use them. So you need to be really careful of that. And once they do learn how to use those tools, they can be really functional in the shop. They can take care of just about anything you need them to do. Also, I wanted to talk about drawings a little bit. I think everybody needs to learn how to sketch. If you want to be an engineer, we used to all have to go through a drawing class where we would sit at a drafting table and we would draw things with pencil. And that was really neat that we learned how to do that. But that's not done too much anymore. You get on a computer and you do everything on CAD, and CAD's really great. But when you're in the shop and you're trying to explain something to somebody, it's really nice to be able to get a piece of paper and a pencil and draw an isometric drawing and say, well, this is how this is going to go, and this fits over here. And being able to do that is really nice. So, and most of the time when you're learning to draw things like that, especially in isometrics or orthographic projection, you end up throwing a lot of your work away because it just doesn't look good. And that's normal. It's like learning to play the piano. You don't start really doing very well. So I recommend that you get a sketchbook, and it can be simple as this. And you make sketches of all the things that you're working on, and you can keep your dimensions on there. Quite often, you're away from the shop and you need to know what the wheelbase is or the distance between a wheel and a body or something. And having all those sketches with dimensions on it is a really benefit. So that's something you need to try and learn to do. You also need to learn to do schematics. Now, electrical schematics can be really daunting, but if you take one little circuit at a time, battery to a tail light or battery to some kind of switch that powers something or turns something on or off. If you just isolate it into little things, it makes a lot more sense. And there are all kinds of different schematics. There's point-to-point schematics where you have every little wire goes from one point to another point. And then there's ladder diagrams where you have a ladder and you have lines going across from the power source to the ground, and in between you have the components. But when you have a schematic, you can figure out almost always where your problem is. And if you mark your wires properly, either with color code or at the end of each wire, you can have a little tag that has a number, and then you number the wire on the schematic. That kind of thing makes a big difference. You can troubleshoot your electrical problems quickly and easily. It's such a frustration. And we had a lot of trouble with running wires through tube, and then we would drill into the tube to mount something, and we'd drill into the wire. So be very careful that if you're going to run a raceway for your wire, I recommend you use something that's non-conductive. And you can get the surface mount raceway at Home Depot and Lowe's, and it glues up wherever you need it and unsnaps, allows you to get to your wire. So, you know, taking care of your wiring is really a big deal. It becomes a rat's nest really quickly. You have lots of wire all over the place, and you can't tell where things go. I worked for a company that they used only white wire on their vehicles. This was a company that built all kinds of oil field equipment, and they would have something like 3,000 wires, and all that wire was the same color. It was all white. But they had a machine that they would pull the wire through, and it would stamp two numbers on the wire. It would stamp every 6 inches. It would stamp a wire number and the size of the wire, whatever the wire gauge is. So that if you were underneath this 40-foot trailer and there was a bundle of wire and that wire had gotten snagged and broken, you could get the number off of it, go to the schematic, and instantly know what wire you're going to have trouble with. So things like that make a big difference when you're trying to troubleshoot your problems at the track, and you will have trouble. Everybody has trouble. So things happen, but try to avoid running wire through something that's conductive just to hold it. Like on our array, we ran all the wires through the tubing, and that ended up being a problem, so I don't recommend that. So after you've got your design done, you're going to want to build a chassis. Everything on the car bolts to the chassis in one way or another. The chassis supports everything. And there's three basic types of chassis. One's a ladder frame, one's a space frame, and one's a monocoque. The ladder frame is like it says, it looks like a ladder laying on the ground. Examples of that would be like a Model A Ford or a go-kart frame. They're just flat with wires run across. So that particular design is not bad, but it has very little structural rigidity, no torsional rigidity. If you take the front and the back of one of those and you twist it, you can twist the go-kart frame pretty easily. So that torsional rigidity needs to be there so that when you take a lot of time to make your suspension line up, it stays lined up. If you go around a bump or something and the chassis is moving around, well, your wheels are moving around too. So it's important that you have something that has some rigidity. A space frame is kind of like a ladder frame, one on top of the other, separated by tubes. It has quite a bit of torsional rigidity. And to explain torsional rigidity, if you take a shoebox and you take the lid off the shoebox, you can twist that shoebox pretty easily. If you put the lid back on, it's pretty stout. It doesn't want to bend very much. It doesn't want to twist. That's torsional rigidity. The ultimate in structural torsional rigidity is the monocoque. The monocoque in the car industry is called unibody. So the skin on the outside is actually the frame. Example of that is just about every airliner that you ever have been on. Those planes are all monocoques. They're tubes that have lots of structural rigidity. Now, a monocoque can be made two ways. It can be made with aluminum sheet metal or steel sheet metal for that fact, but and it can also be made out of composite. So an example of sheet metal would be an airplane, and example, composite's an airplane, then I'll make all airplanes all out of composite too. The difference with the sheet metal is that it can be folded pretty quickly, and then you just have to drill holes in it to mount things. The composite takes a kind of a mold to put it in. It's a lot harder to build. And the car you saw outside, that's an excellent example of a monocoque composite construction. Sheet metal is a lot more forgiving. You can actually make some modifications to a sheet metal monocoque, whereas a composite, you can't make any corrections. Once you build it, yeah, that's what you're going to have. So in this case, it's really nice to build a prototype and play with that. In our case, last two cars we built, we made plywood mock-ups of the cars, which helped a lot because the students could sit in the car, they could see how much elbow room they were going to have, if they had any, and where things were going to mount. How much room did they need for their feet? How much room do they need for the steering components? And so we built quite a bit of stuff out of plywood. And when you're starting to, of course, plywood's really inexpensive and easy to change. If you don't like it, you can just make firewood out of it. The other thing you can do with building things on a plywood and cardboard, if you're trying to decide how to mount your batteries and how do you mount some other component, you can make a little cardboard template of it and put that in there, and that helps a lot. And in fact, in the aerospace industry, sometimes you're required to make a cardboard template and go see if you can actually fit it down inside the fuselage with everything mounted in the plane. This is true of like even the Lockheed fighters that they build. You have to kind of go through a proving system. So you can't just do it all on CAD. Sometimes you actually have to make a component and go see, well, will this actually fit in here? And so we did that several times on our batteries, and it helped us determine how to mount the batteries. Back to the skills, teaching kids to use tools is a big deal. If you teach them how to use these tools, even these hand tools, they'll always remember that. They'll always remember how to do that. And as you go through life, you're always going to need to take a screwdriver or a wrench or something, and just the ability to use that and know how to use it is a big deal. So you need to take time to do that, to teach them how to properly use the tools and how to use them safely, not to take a hammer and hit something the wrong way. In fact, not to use a hammer much at all on our cars, and how to measure angles and what you can do with a piece of string. It's amazing what these things can do if you'll use them. Your designs for the car, we talk a lot about designing a car. You have to remember that these things are road vehicles. So you're going to be bouncing over things. You're going to go over curbs. You don't want to go over curbs, but they're going to be driven over curbs, and they're going to run into 2x4s on the ground and things like that. And consequently, you're going to get an impact load. So if you've got a 50-pound battery and you're mounting it with some small screws, and that looks pretty good, and you maybe use some Velcro on it or something, well, the first time you hit a bump, that's all going to break. So you have to remember that in a road vehicle, anything that moves, you've got an acceleration from the gravity, you've got impact from things you're going to run over. So you've got it designed for about a 2 to 3 times weight, whatever the weight of the actual thing is. I think that's one of the biggest things. Most of the failures I see are from people that don't realize how much the impact load is going to be when they take it off a trailer, when they put it back on the trailer, and you'll actually see suspension parts break. So you need to pay a little bit of attention to that. If you're going to select bearings, the bearing books are on the internet. You can find all kinds of descriptions of the bearings. They all have a radial load, and they have a load capacity for static, and they have a load capacity for dynamic. And the static is usually lower than the dynamic. But those are the places you need to find what the maximum load is for that bearing and you'll have to figure through trigonometry what the load's going to be on a shock absorber mount, things like that. And all these things that you're going to mount your shock absorbers or your springs or your steering components, they're all going to have some components like that that get loaded from impact, and you got to keep that in mind. Welding, for the most part, welding doesn't take much of a weld to hold the load. Welding's pretty strong. Monocoques are a little bit different than that. You have to sometimes add additional bracing, and sometimes you have to build a superstructure that comes up to that point and attaches to it to help take the load. But on welded parts, normally, if and there is a way to calculate that, you'll need to learn to do that. But all the materials are rated in pounds per square inch. Everything is rated in pounds per square inch, and it's usually a tensile load trying to pull it apart or a compression load trying to put it back, push it together. And so you'll know if you have 100 pounds of load, you're carrying something that weighs 100 pounds, and you're going over a bump and get about 3 G's of acceleration on it. So instead of 100 pounds, it's 300 pounds. Well, how big a weld does it take to support that? Well, you can figure out that it's so many pounds per square inch. Steel is typically around 20,000 pounds per square inch for a weld. So you can take those things you can take those things and calculate how big a weld you need. And if you'll do that, I think you'll find that welding works pretty good. You don't always have to. I see a lot of people that make a nice weld and then they grind it all the way, make it nice and smooth. They don't necessarily want to do that. You normally will weld something, have a nice fillet or a nice raise on the weld, and then that's it. And most of the chassis that we see are built with MIG welding, which is a really good process, but you can also braze these things. The industry for building race cars over in Europe, they all use brazing to put their vehicles, their tube structures together, and they're usually nickel bronze welded. So being able to braze something is a nice way to put thin materials together, and it holds up really well. I don't have a whole lot more. Are there any questions about building a car? No questions. How many people have their design already for their chassis? Is anybody building a tube frame? Have you done a structural analysis on it, like a FEA, finite element analysis on it? Okay. But you can do that. You can actually go to each little triangular section and you can calculate for each section, which is a statics problem, but that's the way to do that, and figure out what kind of bracing is what it's gonna take, what items are in compression and what are in tension. And the gentleman on the end there from Fort Worth Christian, you had a question? What?
Yes, you use brazing on your frame.
A lot.
Okay. And what was the base metal that you were?
Any kind of steel. I mean, brazing is kind of interesting. You can take a galvanized tube like you're going to have from conduit. There's a lot of mounts you can make out of it. Pretty decent tubing. And you can braze those. You can't weld them really, particularly, because of the zinc that's on it for the galvanizing. But you can braze that. And one thing about brazing anything that's got zinc on it, it gives off a little green gas when you do that. You want to make sure that you have ventilation and don't breathe that gas, because that's phosgene gas. It's what they used in World War I. So it's a dangerous gas. It's poisonous. And you're not going to generate very much of it, but you want to have ventilation when you're brazing something. But it's a great way to build little brackets, an excellent way to take little tube sections and put them together and that you can bolt through. It's a really great way to mount things. Any other questions? How many?
Add on to that, just from what I've seen with cars and personal experience, I agree that that's something you can do that is handy for sometimes making, when you want to still be simple, but maybe make a more complex bracket or part that you're going to use on your car. That is a good way of getting things stuck together so you have that complex shape without a lot of extra work. For structural components, if you're looking for one of the most simplistic and basic ways to do it, at least I personally would strongly recommend mild steel and MIG welding as a starting point. It's heavy, but it's very easy to pick up and learn without a lot of extra training. Even to figuring out how to get good penetration on MIG welds, it doesn't necessarily take that long. So for like an introduction to basic welding, and a lot of schools I know have automotive shops and welding tech classes and things like that, but MIG welders are pretty cheap to get into, and it's a good way to start a structural car, because one of the biggest killers I see of new cars is under-designing it, meaning that we tried to go too light. We didn't test the car. We built it and thought it was going to be good enough. If you can't get to doing like a finite element analysis, which I know can be daunting for some people, but if you just don't know and you don't ever put the car out on the road, what happens is by the time you get here, either A, brakes on your trailer during the long drive out here, or B, as soon as you start doing scrutineering, it brakes on you. Or C, if it's a road race, you make it halfway through day one and then you break down. My recommendation to first-year teams and new teams, at least, again, this is my experience over the last 25 years, is mild steel is pretty easy to work with. You can build whatever you need with just a few tools, and to overbuild. Yes, weight is terrible because you have to carry more weight with you and you're going to be less efficient. But I guarantee you, you will beat about half the competition here if you have a car that just makes it to the end of the event versus a car that's 350 pounds lighter that fails on day one. So all this, and I'm sorry for jumping in, just to say that I believe that's one of the good ways to get started with something for structural components is just simply mild steel. It's readily available, and MIG welders are pretty easy to find, somebody that can show you how to start.
Yeah, the welders are now much less expensive than they used to be. You can buy a really good MIG welder for a couple, $300, $400, and it'll get you through this car without any problem. And really, mild steel is a wonderful material. It's really resistant to fatigue cracking. You're going to have fatigue cracking in chrome moly pretty easily. You have to treat it a certain way or you'll get fatigue cracks, and you won't have that with mild steel at all. It's a good material. So you just have to be kind of logical. I mean, you don't want to take something that's ½ inch thick and weld it to something that's, 1/8 of an inch. I mean, that's not right. You want to keep the sizes of the material about the same, the thicknesses. And anything that's a 65 thousandths thick or 83 thousandths thick in a mild steel is plenty good for a chassis, and it'll last you a long time. It's very serviceable, very repairable. So, okay.
Well, thank you very much.
Welcome.